Good afternoon and even good evening, because we have people from different parts of the world studying in this life. Thanks to Dr. Chris Mckay. Dr. Chris Mckay, you would have seen him in many of these documentaries on the origin of life. He's a very well-known scientist. So let us hear from Dr. Chris Mckay. He has a lot of interesting things to share with us today.
Full screen. Here we go.
Yes, we can see you.
Okay. All good? Okay. So what I'm going to talk to you about today is the search for a second genesis of life. The word of is missing there. Second genesis of life on other worlds in our solar system. And I emphasize that, I will through the talk, that we're not just searching for life. We're searching for a second genesis of life. And I'll explain what I mean by that. And of course, you know the date and you know where we are. So let's go. What is a second genesis? This is an important concept, and it has implications scientifically and also in terms of how we search. What I mean by a second genesis is life that does not share a common origin, genesis, with life on Earth. Life on Earth is this tree right here. The green, the red, and the blue branches, the tree of life. You're probably familiar with this from your biochemistry and biology classes. If not, just search on the tree of life. This tree of life tells us that all life on Earth relates to, shares a single common origin, single common genetic code, and all life on Earth can be mapped into a single phylogenetic tree. Now, you'll notice that the viruses are not on this tree. It's a particularly hot topic, I guess, today, this time. But still, the viruses fit within this system of genetic and information that all life on Earth shares. There's only one type of life on Earth. Are you still with me?
Yeah, we can hear you.
Okay. If we have, what we're looking for is a second genesis, is something that is not on this tree of life. So aliens, as I define it, is any organism that is not on our tree of life. Now, why is that interesting? Well, we would then be able to do comparative biochemistry, and it would tell us that life is common in the universe if we found two examples of it here in our solar system by a rule that's sometimes called the 0-1 infinity rule, which is the rule that the only numbers in the universe that make sense are 0, 1, and infinity. And when it comes to life, we know we're at 1, not 0. If we could get to 2, that's as good as infinity. So I want to get to 2. So we're searching for another example of life that represents a complete separate origin of life than life on Earth. In other words, is not on our tree of life. So that's the practical definition. Operational criteria, we go find life on another world. We say, is it on our tree of life? No, then it is the second genesis. So where to look? There's really 4 targets. Our solar system is not a very good place for life. It's actually miserable. There's only one planet. Fortunately, there's one. There's only one planet that really looks pretty good, and that's Earth. We should keep that in mind, of course. The other planets are a poor set of planets for life. But the solar system, it's the solar system we've got. It's the one we've got to live with. It's the one we've got to explore. It's kind of like family. We don't get to choose them. They are what they are. Right? So these are the worlds we can explore. Now, I'm not going to talk about searching for life, for a second genesis of life on exoplanets. On exoplanets, there's thousands to choose from. But we can't get a sample of life from an exoplanet. We can't map it on our tree of life. It is not, we can't really do a search for a second genesis. So these are the worlds, and I'm going to talk about 2 of them primarily, Mars and Enceladus. I've marked on each of them an icon to indicate, in some sense, how the opportunities are for searching for life there. Mars gets 2 little red stars. There's 2 ways that we might find life on Mars. It'll be hard, but we might find it. Europa gets a black X. It's got an ocean, but it seems to be locked away from us through a thick layer of ice. Doesn't look like it's anything we're going to be able to get to anytime soon. It's just too hard. Enceladus, little moon of Saturn, gets a gold star. It gets a gold star because, as I'll show you, it is the best target. It's the one that looks like we're going to be able to do it pretty soon. Titan gets a question mark and an exclamation point. It gets a question mark because Titan is the only world besides Earth that has liquid on its surface and beaches where the liquid comes up to the land. But that liquid is not water. That liquid is liquid methane. And we have no idea if there could be life in liquid methane. That's the question mark. The exclamation point is because if there is life on Titan in liquid methane, then it is certainly and obviously a second genesis. There's no way that life in liquid water on Earth is related to life in liquid methane on Titan. So finding life on Titan would be the best possible answer from my point of view, because not only would it tell us that there's life, it would tell us that it's clearly a second genesis and that there's life in the universe and that it's diverse. That here in our own solar system, we've got one type of life that's weird and another type of life that's normal, maybe normal. Now, we don't know who's weird and who's normal. Maybe Titan is normal and we are weird living in water. But the fact that there's such 2 different life forms tells us that life is common and life is diverse. That would be very cool. That's the exclamation point. I'll mention a little bit about the mission that we're working on for Titan, Dragonfly, that will take the first preliminary steps in the search for methane life on Titan. Let's start with Mars, of course. It's the planet that always gets the most press, the most attention, most spacecraft, the most money. Mars, here's a one slide explanation of why Mars is so interesting. Early in its history, Mars, we think, looked like this, and you can see it compares to Earth. At one time in our solar system, we may have had 2 blue marbles, not 1 blue marble like we have now, but 2, 1 Mars, 1 Earth. That may have lasted for 500 million years. And then the lack of plate tectonics, less gravity, and no magnetic field, Mars lost its atmosphere and became cold, dry, lifeless, apparently lifeless. All these factors trace back to the fact that Mars is so small compared to the Earth. It's 1/10 the mass of the Earth. So in a nutshell, this is why Mars is interesting. It was very much like Earth early in its history, and then it died out for reasons we think we understand that relate to the size. So I want to talk a little bit about the mission that's on Mars right now, giving us information about its early history and the possibility of life. Curiosity, the big rover, it landed on Mars in 2012, and it went to what I think is the most interesting place we've ever been on Mars, which is the bottom of a crater, Gale Crater. And the particular area in this photograph at the bottom of that crater is called Yellowknife Bay, and it is a dry lake bed. So the rover is standing out looking over a dry lake bed. That is so much more interesting than anywhere else we've been on Mars. All the rocks we are looking at in this picture are mudstones. They're mud from the bottom of a lake compacted to make it hard, to make it mudstone. All the other places we've been on Mars, the rocks were volcanic rocks, basaltic rocks. Not very interesting from the point of view of life. Mudstones are very interesting. So the rover is standing on the bottom of a lake. If the rover had gotten there to this site 3.5 billion years ago, it would be underwater. It would be swimming. And what kind of lake would it be swimming in? I think I can show you a lake that is an example of what this lake on Mars was like 3.5 billion years ago. 3.5 billion years ago, this lake formed from an impact, filled with water, and formed these sediments. Now, this is an artist's conception of it. When artists draw pictures of early Mars, they never put the ice in. So I have to add it myself with Photoshop. Even when Mars was wet, even when it had lakes, it was cold. The lakes would have been ice covered, but that's fine. Here's an ice covered lake in Antarctica that I think is a model for what this lake on Mars could have been like. And we are studying it and the life that's in this lake. On the shore, up here on the sides, there's nothing. It's dead. It's too dry, too cold for life. But this lake, which is ice covered, this is our camp in the warmest time of the year, the December, January. It's the warmest time of the year, and still it's completely ice sealed. This is our camp. The lake, the ice on this lake is 3 meters thick, and then beneath that ice, there is 100 meters of water in the middle of Antarctica, very remote part of Antarctica. Now, just for some side interest, once we were there a couple of years ago, we got a visit from some geologists from the Indian station, Mckay, which is not far from the site. And it's India's second permanent research station in Antarctica. These were glaciologists, and you can see the guys with the red top parkas. They are the glaciologists from the Indian station. India has a very active Antarctic program and a base very close to this, well, very close, about a 5-hour drive by truck from our site in Antarctica, where we study this lake. There's also a Russian base nearby as well, Novo Station. Well, what we're interested in this lake is not the ice on the top, but the water underneath the ice. So we drill a hole and we take measurements. People have done this before at this lake, not very many. This lake is very remote, but people have done it before. But then we did something that no one had ever done before, which was go into the lake. We cut open a hole in the ice, and then we were able to dive in the lake. This is a picture, in fact, of me getting ready to dive down into the lake in a dry suit. You see the line connecting me back up to the surface. And being able to go into the lake allowed us to get the big picture. And the big picture was quite amazing. On the bottom of this lake, there are structures built by microorganisms. These are pyramids. Think of these as pyramids. They are about 30 centimeters high. They're not that big. But to think of them as pyramids, remember that these are built by organisms that are 1 micron big. So these pyramids are 30 million times larger than the organisms that build them. On that scale, the pyramids in Egypt are tiny compared to the relative size of humans. So these microorganisms build these massive structures. They are not found, these conical structures, conical microbial mounds, are not found in any other lake in the world. There are microbial mounds in other lakes, but not this particular conical shape. And they are found in the oldest fossil record on Earth in the Pilbara in Australia. So we think these mounds and this ice-covered lake is a model for early Earth and early Mars. Now, the reason these mounds are formed here and nowhere else is because this lake is so isolated. There is nothing but microorganisms in the lake. There are no fish. There are no tadpoles. There are no amphibians. There's nothing that would eat or disturb the microbes as they go about their life cycle and mound building activities. So they can build these structures unmolested. If these organisms were living in a lake here in California, fish would be eating, grazers, plankton, zooplankton would be eating these microorganisms and these diatoms, and there would not be mounds forming. So it's the isolation of this lake that allows us to see back in time on early Earth and we think on Mars. So back to Mars now. These mudstones are the bottom of a lake. If they are the bottom of a lake like this in Antarctica, then these mudstones should contain the remnants of these microbial mounds in this mud. So when Curiosity reached this mudstone on Mars, I was very, very excited because we'd been working at this lake. This was a very good analogy. This mudstone should be perfect. Drill into it, get below the red stuff at the surface. The prediction is it would turn black and it would contain remnants of biology from 3.5 billion years ago. Well, that was almost right. When we drilled into it, it did turn black, dark. It did have hydrogen sulfide. It did emit hydrogen sulfide when heated. It was all indications of an anaerobic mud, just like the bottom of a lake. But we didn't see any strong sign of biology, any strong sign of organics at all. Organics at very, very, very low levels. What's the problem? I think the problem is exposure by radiation. Cosmic rays have destroyed the evidence of life here. So let me just do a sound check, and can everybody hear me?
Yes, we can hear you.
Great. Just checking. Okay, because we're about to move from Mars to the outer solar system. So Mars is interesting. Now let me back up to Mars. What we need to do is go back to this site or sites like it and drill deeper. We need to go deep enough that we can get below the level that cosmic rays would have destroyed the organics. With the thin atmosphere, no magnetic field, Mars's surface is shelled by cosmic rays. They destroy the organics, apparently. We got to get deep. We need to go 10 meters down at this site. That's why Mars gets a little star. There may be evidence for life there, but it's going to be hard to get to. We're going to have to get a drill that can go 10 meters down. Easy to do that on Earth. Easy to get to 10 meters on Earth. Very hard to do it on a robot on Mars. Okay, let's move away from Mars. We're going to still try to do missions there, but now Enceladus. Enceladus, this is a picture of the Saturn system showing the rings of Saturn. Very beautiful. Go look at them in a telescope, please. And you see the Enceladus, one of the little moons out here, Enceladus, and the faint, very faint E-ring that's associated with it. Right? The E-ring, the presence of the E-ring was the first hint that Enceladus might be active. And that was in 1960s when the E-ring was discovered. They realized that maybe Enceladus is active. But the real surprise came when Cassini flew by Enceladus 2005 and discovered jets of water coming out of Enceladus. So here's Enceladus, a moon about 500 kilometers across, very small, with a jet of water coming out, like a squirt gun into space. Well, it's a really big squirt gun. The flow of water out of Enceladus is volumetrically equivalent to the flow of water in Old Faithful Geyser in Yellowstone Park. It's a lot of water coming out. But even more interestingly, that water is coming from a hot pocket of water, an ocean, not a pocket, an ocean, that's in contact with hot rock. So hydrothermal systems, hot water, hot rock, reacting, forming interesting compounds, pressurizing the water, shooting it out. And when Cassini flew through the water plume and measured it, it's not just water, it's soup. It's got methane, ammonia, organics, all the compounds needed for life are there. There's carbon compounds, organic material, there's nitrogen in biologically available forms. There is a chemical energy, redox pairs like CO2 plus hydrogen that microorganisms can use. And there's evidence that it comes from a hydrothermal vent. It is, all the boxes are checked. All the boxes are checked for life. Water, carbon, nitrogen, energy. The four big requirements for life. They're all checked. And the samples are right there. We don't have to drill 10 meters. We don't have to get through 10 kilometers of ice like on Europa or drill through 10 meters of dirt like on Mars. It's coming right out into space. There's a big sign, free samples. We just got to fly through and take them. So that, I think, makes Enceladus very, very interesting. And that's why Enceladus got a golden star on the list of the planets. It's the one that I think is most likely to tell us a story that's going to be very interesting with respect to life. So we are working on mission designs to go to Enceladus and fly through the plume and analyze it. But I think that to really make a compelling story about life, we need to bring the sample home. So one of the things I've been working on is bringing a sample back to Earth from Enceladus. And we are trying to propose this as a joint U.S.-Japan mission to return a sample to Earth. The reason U.S. and Japan is because those are the two countries that have done sample return from beyond the moon. Stardust and OSIRIS-REx are U.S. missions that Stardust brought a sample from a comet back to Earth. OSIRIS-REx will bring a sample of an asteroid back. And Hayabusa and Hayabusa 2 are Japanese missions that brought samples back to Earth, samples of asteroids. So the two countries both have experience in bringing back material to Earth from deep space. And the programmatic model for an international mission will be Cassini. In Cassini, the U.S. built the main spacecraft, and Europe built the Titan probe. In the proposed model here, Japan would build the return capsule, and the U.S. would build the main bus. But there's a challenge here, a major challenge, and this picture shows that challenge. This picture is another U.S. sample return mission from beyond the moon, which I didn't put on my list, called Genesis. Genesis returned a sample of the solar wind, and it crashed on landing. The parachute failed to deploy. Well, that's okay if you're bringing back a sample of the solar wind. Nobody cares if it crashes or not, except the scientists involved. And they were able to get a lot of the science out of the sample anyway. It wasn't completely destroyed. But if you're bringing back a sample from a world like Enceladus, from an ocean that's very much like our ocean, in which you hope the sample would contain something that's alive, then an outcome like this is very, very problematic. The risk of crash on return would be disastrous. It basically cannot be allowed. You have to return a sample, an astrobiology sample which might contain life. You have to basically return it with no chance of failure. So how do you do that? How do you return a sample that has, which might have life in it? I think there's two possible solutions. One is don't return it to Earth. Return it to Earth orbit or close to Earth, and then send astronauts out to get it. Right? And that has several advantages. One is astronauts, by definition, are in a human-rated vehicle. That means the vehicle's been tested a lot more than robotic vehicles. And second, more importantly, there's a human-in-the-loop safety system. If something's going wrong, the parachute's not deploying, the astronauts are going to notice it and fix it. Right? The human-in-the-loop safety system has been critical in saving many human missions and just in history already. Humans can notice that there's a problem and fix it in ways that the autonomous systems cannot. But we can't propose to use astronauts because that's a different part of NASA. We can propose to work with Japan, but we can't propose to use astronauts. So we have to come up with a robotic system that's 100% fail-safe. We can't use astronauts. We have to do it robotically, but it has to be 100% fail-safe. So how do you do something that's 100% safe? Well, the short answer is if you don't move, don't think, and don't make any decisions, you will never get into trouble, right? And that's the philosophy we'd apply here. So make your entry capsule so it has no parachute. So you can't fail to deploy a parachute. It has no parachute, has no computer, has no deployable mechanisms. It literally is designed to crash. All it has to do is obey the law of gravity and crash into the Earth. So it lands at terminal velocity, which would be about 100 miles an hour for a small object like a capsule sample return. But you design it to survive that. And we know that that can work because meteorites do it all the time. Meteorites land on Earth, small ones at least, ones the size of your fist. will slow down enough that they can land on Earth intact. Stony meteorites can land on the Earth intact. Even carbonaceous chondrites can land on Earth intact. They survive landing. They deliver organics to the surface of the Earth. The interior of the meteorites is still cold when they land. So we design it like a meteorite. The sample we're bringing back is very tiny. So basically, think of something the size of a softball or a baseball, with inside of it a couple cc's of Enceladus Ocean, and it's designed to be like a stone, and it lands like a stone. There's no computer, there's no parachute, there's no fins, there's no ailerons, there's nothing, no rockets, no jets, no attitude control. All it does is just coast down. The good thing about that is you then know exactly where it's going to land, and you can be there to catch it. No drifting on the parachutes. So we've got the sample. How do we know that it's alive, or that it was alive? How do we recognize alien life? Right, well, if you look at the literature, here's the literature. Use a tricorder, or we'll know it when we see it. That's from Calvin and Hobbes, and Star Trek, of course. Well, we don't know how a tricorder works, and if it's microscopic, we're not going to recognize it. It's not going to be green and jump up and chase us. It's not obvious how we would recognize alien life. How would we recognize the second genesis of life? How would we recognize it if it was dead? Suppose we bring a sample back from Mars or a sample back from Enceladus, and it contains the remains of organisms. They're dead, but they're there and they're alien. How do we tell? This is a very important question, and I don't know the answer. I have a suggestion. But those of you interested in biochemistry ought to think about that question. How do you recognize alien biochemistry? Or, asked another way, if we find organic material on Mars, Europa, Titan, or Enceladus, how can we tell if it was ever alive? We're not really interested to know if it's alive or dead. We're interested in if it was ever alive. Dead is fine. Something that's dead is evidence of life, because you can't be dead if you weren't once alive. Right? Now, if it's like us, if it's part of our tree of life, well, it's easy. We just look for DNA. If you take a sample to a lab and say, is this or was this ever alive? They'll just look for DNA. If they find DNA, they'll say, yes, this was alive. If they don't find DNA, they'll say, no, it's not alive. But if it's alien, it might not have DNA. It's unlikely to have DNA. How do you tell that it's alive? Or here's a way of making the question really specific. Here are 3 pictures of organic material. One from a meteorite that landed in Australia. One from a laboratory experiment by a high school student working in my laboratory, doing a Titan simulation. And one, flowers in a garden, and organic matter around those flowers, which is dead organic matter. In the first 2 pictures, the meteorite and the Miller-Urey experiment, there's nothing alive in that organic matter. There can be amino acids in the meteorite, amino acids in the Miller-Urey experiment, but they're not biological, and they never were biological. It's not just not alive, it's not dead either. It's not any more dead or alive than a rock. They are non-biological. Now here in this picture, we have life. We have life that's alive, and we have life that's dead. In the soil, we have the remains of organic material. It's dead biology. And in this plants, we have biology that's alive. But they are both biological in origin, the dead and the alive. The quick and the dead are both biological in origin. Is there a difference between organic material of biological origin and organic material of non-biological origin? The answer is yes. And the best example of this is the amino acids. We find amino acids in life, we find amino acids in the meteorites, and we find amino acids in the Miller-Urey experiments. The difference is, in life, in the proteins, there are only left-handed amino acids. In the meteorites, both left and right appear. The mirror image of the left is the right, D for dextrose. The right-handed and the left-handed amino acids occur both in Miller-Urey experiments and both in meteorites. In biology, only left-handed amino acids are used in proteins. There's some use of other D-amino acids and other things, but not in proteins. So the majority of the amino acids in your body and the majority of the amino acids in life on Earth are left-handed. So this is a test. This is a test we can apply. If we go get organic matter, we look and see what amino acids are there. There's many more amino acids than the 20 used by life on Earth. So life could have different amino acids. This strange biology or even stranger biology could be based on different amino acids. Or they could be based on the right-hand side, mirror image. So here's the mirror image of Earth's amino acids. Instead of left-handed, right-handed. Some people call this anti-life or mirror life. Right? And there's some science fiction stories about mirror life. An episode of Star Trek where one of Spock becomes a mirror life form. So it's exact, everything is in the mirror, like Alice in Wonderland through the looking glass. Okay, so another world, Titan. This is a picture, a scene from a BBC show about Titan on the beach. Titan is the only world besides Earth that has huge bodies of liquid on the surface, but the liquid is liquid methane. These are the lakes in the northern part of Titan. Could there be life in Titan? Well, we might find out soon. We recently were approved, NASA was recently approved to fly a mission called Dragonfly. This is an 8-blade drone that will go to Titan, and it'll do a lot of things, but it'll do two things that I think are the first step in the search for life. It will search for variation in hydrogen, and it will do use a mass spectrometer to search for evidence of molecular selectivity, like left versus right amino acids. Why is searching for hydrogen a sign of life? Let's think about life on Earth. So life on Earth is based on carbon, lives in liquid water, and because carbon is widespread and liquid water is widespread, life is widespread. It's all over the planet. Because it's widespread, it affects the planet globally. In particular, the gases in the atmosphere, oxygen, methane, and CO2, are all produced by biology. Let's take CO2 because it's a very interesting case. If you looked at the Earth from outer space, you would say, oh, that planet has about 450 parts per million of CO2, and it's going up, right? But if you looked at the CO2 in detail on the ground, flying through a street in the city, in somebody's house, out in the woods, in the backyard, summer and winter, you'd find that the CO2 is going up and down and up and down. Inside your house, it can be 10 times what it is outside because there's people in your house breathing out CO2. You go through the woods in a spring morning, and the CO2 can be dropping down because the plants are taking it up. It goes up in the winter when plants shed their leaves. It goes down in the summer when the plants take it up. So there are diurnal, local, and seasonal changes in CO2 that can only be explained by biology. CO2 has no sinks or sources that could cause those changes spatially, daily, seasonally, other than biology. So if you were to fly through the planet Earth on a drone measuring CO2, you could make the case that you're seeing the effect of life on that planet. You can't do that so easily with oxygen because there's too much oxygen. It doesn't vary hardly at all. And methane, you could do it, but you don't see there's not enough methane. You can't see, you have to go to certain places to see methane, right next to a cow or near a swamp or a landfill. But CO2 is perfect because there's a background level and there's variations with respect to that level that are significant and due to biology. On Titan, we have the same situation. Life is carbon-based. There's a lot of liquid methane. If there's life in that liquid methane, it would be widespread and it would affect the atmosphere, and you could see it in the hydrogen. If there's life on Titan, it is eating hydrogen. Here's why. The energies that can give you, the chemistry that can give you energy on Titan is chemistry of hydrogen. On Earth, it's oxygen. We humans breathe in oxygen. We take in organic material. My preferred organic material is chocolate. We consume the organic material with the oxygen, and that gives us energy. On Titan, that doesn't work because there's no oxygen, but you could react that same chocolate with hydrogen on Titan and get energy. Now, there's no chocolate on Titan, but there is acetylene, which is for many microorganisms even better than chocolate, and ethane and even tholin, the solid stuff. So on Titan, chemical reactions that can release energy comparable to the energy that methanogens on Earth need, for example, all involve consuming hydrogen. So life on Titan is going to eat hydrogen. That's the prediction. So that's what we would search for. Okay, now I want to wrap up, hopefully with time left for questions, by asking a question that a student asked me. A few years ago, I gave this talk, similar talk, in Death Valley, appropriately named Death Valley, to a public audience. And after the talk, a student, she must have been maybe 10 or 12 years old, asked me, well, what do you do if you find a second genesis of life? I said, that's a really good question, because we spend all this time figuring out where to search and how to search and building missions to search, but very little thought about what do we do if we find it? What if we find a second genesis, and Mars in particular? And it makes me think of a dog chasing a car. You could ask the dog, well, what are you going to do if you catch the car? Right? The dog is unprepared for success. And we have the same risk. We're searching for life on Mars, a second genesis of Mars. And yet we haven't really thought through, what does it mean that if we find it? What does it mean for plans to send humans to Mars? What does it mean for notions of terraforming Mars? What does it mean for us as life form on Earth, life form 1.0, to suddenly realize that there's life 2.0 next door? And maybe life 2.0 is in trouble, not doing very well. There's a lot of questions that we don't really address. We're just going for the search without thinking about it. If you do think about it, I think there are some interesting implications that rest on the question, what is the moral status of alien microbes? If we find a second genesis in our solar system, there will then be more than the usual sets of moral consideration, which on Earth at least include humans and life. If you kill another human, you are doing something that's morally wrong and criminally punishable, mostly. If you kill other types of life forms, you don't get criminally punished, but it's considered a bad thing to do. We have some reverence for life in general, some cultures more than others, but the idea is still an appreciation that there's something special and that deserves moral regard in all of life, right? And humans are a particular set that deserves even more moral regard. Well, what if we find another set, life 2? And what if the only examples of that life are microbes? So microbes which score low moral status based on pain, complex behavior, and communication, which are the usual ways of ranking animals in moral consideration. Microbes are on the bottom of that list, but they would have high moral status as being the sole representations of this other set of life. Very interesting. I'm not going to dwell on that. And you might think, well, this is just sort of idle philosophy that the religious scholars can contemplate in their infinite free time. But no, I think this has implications for how we do our space missions. And in particular, I think it implies that we should do our exploration of Mars in such a way that is what I call biologically reversible. You're all familiar with the undo button, Control Z. What a wonderful concept. In my mind, it is the most important conceptual contribution to world culture of computers. The idea of undo. Think of all the times in your life you'd be able to undo something you just did. Fortunately, on Mars, everything we've done so far, we can undo. It is biologically reversible. And I would argue that we must be able to continue that approach until we determine whether there is life on Mars or not. If there is, we must Control Z, Control Z, Control Z our way back to what it was like before we went. And we could do that. It wouldn't be trivial, but it wouldn't be exponentially hard either. It would not be as hard as getting rid of the rabbits in Australia. Okay, I want to end with the moon and the Earth from the moon. This is the time period now where the Apollo missions to the moon are 50 years behind us. And at the same time, NASA is talking about going back to the moon. Other countries are talking about going to the moon. Other countries are going to the moon. More countries are talking about going to Mars. I see a golden age coming in space exploration, an international golden age. And I think there's very exciting science questions that deal with very, very fundamental questions about life, our relationship to life, life in the universe, a second genesis of life, and the hope that we may be able to get some insight to the answers to these questions right here in our own solar system. And I really hope that, because if we can't answer these questions in our solar system, then we have to go to the planets around other stars. And they are very, very, very far away. We can look at them, but we can't touch them. We can't really address the second genesis question without either touching them or talking to them. And hence SETI is very important as well. We can't do it by just looking at them. We can answer many interesting questions about exoplanets by just looking at them. But I don't think we'll be able to answer the question, is it a second genesis? With that, I'm going to escape and stop sharing my screen and maybe turn it over for questions.
Thank you, Dr. Chris. Yes, we are now open for questions. On the live screen, you can see a couple of questions. I can read one. This is from Ms. Prerna Singh. In search for water, in the search for life. What if life has different requirements altogether with respect to the universe?
Yeah, this is an important question. We are mostly searching for life like life we have on Earth. As I said, we have only one example of life on Earth. So when we search for life elsewhere, we search for that example. That does not mean that that is the only way to do life. It means it's the only way we know how to search for life. And we run across this problem on Titan. On Titan, there's a liquid that's not water. And we'd like to search for life. We'd like to search for life. But we don't really know how to do it. We only can, when we search for life like life as we know it, we can do a very specific search like L and D amino acids. We know what biochemistry looks like. When we search for life on Titan, we don't have any clue. We have to search very general principles. Conservation of energy, pollution. A general principle is life will pollute its environment. So we search for evidence of that pollution based on energy requirements. So it's a very hard problem, how to search for life as we don't know it. And some people then conclude, therefore, life must be like life on Earth. And I think that's a mistake. When you only have one example, it's premature to conclude that everything is the same as that one example. We may turn out to be the only water-based life for 100 parsecs. Maybe that there's much more liquid methane and liquid this and liquid that life, and we are the oddballs. We are the ones that the aliens will come to look at and say, man, look at this. These guys live in liquid water. How curious. I don't hear you.
Okay, thanks. There's one more question which is in similar line to the previous one. This is from Dr. Sashi. He's asking, do we know how similar the Earth ocean is to the one in Enceladus?
Do we know how similar it is?
Yeah.
Yes, we know.
How similar
we
are the
know.
oceans?
We know that they are similar in some respects. The ocean on Enceladus has about the same salinity as the ocean on Earth. Yep. The temperature is in the same range. It's liquid water. The big difference is the ocean on Earth is mostly full of oxygen. It's aerobic. The ocean on Enceladus is anaerobic. So the ocean on Enceladus is like the water in the vents in the ocean on Earth coming out of the vents, which is anaerobic. It is not like the ocean in the open ocean, which is full of oxygen. So fish, which use oxygen in the water, wouldn't survive in Enceladus. But anaerobic microorganisms, which don't use oxygen, like methanogens, would find the ocean on Enceladus very comfortable.
Thanks. There's one more question which you may be seeing on your screen as well from Sagnik Chatterjee. A very personal question to Professor Mckay. Has it ever crossed your mind that life 2.0 might be hiding from us or supervising us?
Right. That question is the SETI question. SETI question. In order for it to hide or supervise, it must be intelligent. And that's SETI. And I agree that that's an important question. I don't work in SETI because I don't have the temperament for sitting at home waiting for the phone to ring. I have to go out and do something, so I'm going to search. But I think SETI is a very important thing because it is the only other way we will answer the question of second genesis soon. So if they're hiding from us or supervising us, we have to penetrate that disguise and talk to them. And we have to ask them, do you share a common origin with us or not? If they do, well, we're not interested in them. If they don't, then we are. Then it's a second genesis. So the question that motivates me is a second genesis, and it can be answered either by communicating with intelligence or finding an example of life and testing it in the laboratory to compare it to our life. The SETI question is very hard. This is one part of it. Are they hiding from us, or are they there at all? And this is known as the Fermi paradox, and there's much written on it. I don't really have any insight to offer on it. It is not an area that I study or am interested in, but I still think it's important.
There's one question which is going towards the sun. The question is from from Shrabani Patnaik. Maybe no life on surface of Venus, but possibly in atmosphere.
Right. Venus didn't make it on my list, but it could. And there's a growing interest now in possibility of life in the clouds of Venus. But it's not on my list because when I look at the clouds on Earth, they're not full of life. I asked the question, why are clouds not green? Why are the clouds not green? They have water, they have nutrients, they have sunlight. They are, one would think, naively, habitable. But they're not green. They're not full of photosynthetic algae. Why are clouds not green? And that biased me against Venus, I have to say. It biases me against any place where life has to grow in clouds, like the suggestion of life in the clouds of Jupiter or the clouds of Venus. I'm just not optimistic that clouds are suitable. All the life forms I've studied on Earth, I've been on the ground, in rocks, on rocks, or in the ocean. And so for that reason, I tend to look on the ground and in the ocean. So that Venus doesn't look good in that sense. But I admit that bias may be restricting an opportunity. And there are people arguing for a Venus mission. And I say, that's a good point. My response to them is, if you find organic matter, any organic matter, in the clouds on Venus, then I add it to my list too. So far, they haven't found any organic matter yet in the clouds of Venus. There hasn't been a very careful search either. But before you search for life, search for organic matter. If you find organic matter in the clouds, then then all the boxes are checked. Go search. We have found, by the way, organic matter on Mars, and we have found organic matter on Enceladus. Not Europa, not Venus. So clear on Titan, of course. There's lots of organic matter on Titan.
There's one more question, which is about the mounds that you're showing from Moon Chakravarti. What about microbial induced sedimentary structure, if found on Mars, as they are reported in Earth too in shallow water? Are there key points towards life on Mars?
There have been reports, papers, arguing that some of the structures we see on the surface of Mars in the camera images already from Curiosity and Spirit and Opportunity could be microbially produced structures. They're not as definitive as the cones that we see in this lake in Antarctica or the cones seen in the Pilbara, 3.5 billion year old rocks on Earth. But they are consistent with microbial structures. But on balance, people do not find them compelling. We certainly can't rule them out, but if those rocks were on Earth, we would take them back to the laboratory and do careful microscopic thin section analysis to determine are these biological or not. And we should do that on these rocks on Mars too, but we can't. Until we could do that, the pictures we have by themselves are not compelling enough to convince the whole community that there's evidence for life. But they certainly are consistent with that, but they're just not compelling. We need further data, and on Earth, that further data would be microscopic examination and thin section. And maybe someday we'll be able to do that on Mars too.
Yeah. There's one question which is slightly in line with that, from Ankit Verma. If space ethics go by, do we consider terraforming of bodies where there is possibility of life, which we still haven't discovered naturally?
Sorry, what is the question? Is terraforming?
If space ethics go by, do we consider terraforming of bodies where there is a possibility of life, which we still haven't discovered naturally?
Yes, yeah, that's a good point. And Mars is the case is where that becomes relevant. We are thinking about terraforming Mars at the same time we are still searching for life. If we find life on Mars, then obviously we need to terraform it for that life. Right? So if there's life on Mars, it's not doing very well. It doesn't look green. And so I would argue that we should terraform it still, but terraform it for that life. If there is no life on Mars, and if it does have water and all the ingredients needed to make a planet suitable for life, then I would argue for terraforming it and sharing life from Earth. So in either case, I would like to see Mars rich in life. The first choice would be life that's native to Mars. The second choice would be life that we sent from Earth. But we don't know yet which outcome it is, and that is why as we explore Mars, we have to keep open both options. And that's why I argue that we should explore Mars in a way that is biologically reversible, so that we can back away from we have already sent life to Mars on our rover. It's already there.
Yes.
Right? So if we discover life on Mars, we have to pull back that life. We have to Control Z, pull that life back.
Yes. There are a couple of more questions. Do we have time?
I have time, yeah.
Oh, yes, thank you. Right. So the first one is from Samar Saxena. What is the time taken to collect the sample from Enceladus and come back to Earth?
The time, a sample return mission to Enceladus from launch to return is about 25 years. And that's a long time. So when we plan a mission that way, we have already a plan to recruit new scientists in the mission because you just have no choice. But that's okay. This was even true with Cassini. Cassini was a mission that spanned 20 years. When I have worked on Cassini for a long time, for 15 years, 20 years, but it was built and designed when I was still in school. And only when I graduated did I get involved in Cassini. So in a sense, I inherited Cassini. And in a sense, if I'm working on an Enceladus mission now, it will be inherited by another generation of scientists that are not yet even professionals yet. I think that's a good thing. The outer solar system is so far away that the missions are intrinsically intergenerational. And I think that's very interesting. I think somebody ought to do a sociological study of it.
There is another interesting question from Arunatya Das. Can we run experiments as done by Urey Miller in various conditions to understand the formation of organic matter?
Yeah, Miller-Urey experiments under various conditions. People do that. We were doing it. I used to do it in my lab when I had a lab. I don't have a lab anymore. But that I showed an experiment that was actually done by a high school student doing a Miller-Urey type synthesis under Titan conditions. Oh. So yeah, people do it. It's very easy to do a Miller synthesis, a Miller experiment. It can literally be done in a high school science laboratory, and you can change the conditions and change the gases, and there's many different and interesting things to do with it.
Yeah, in that line, there is a question by Adit Narayan. Is there any possibility for chemosynthetic matter on Titan if it consists of water bodies?
Well, there's no evidence of water on Titan, but in the liquid methane, you could imagine chemosynthetic organisms as well. And in fact, if you looked at the table I showed where there's acetylene plus hydrogen producing methane, that is a chemosynthetic pathway. That is chemical energy, and those organisms could use that, would be chemosynthetic organisms. So there could be a chemosynthetic-based ecosystem in liquid methane on Titan. It's possible that there could also be a photosynthetically based ecosystem there. Some sunlight does reach these lakes, but chemosynthesis is thought to have evolved earlier, on Earth at least, and in some ways it is simpler. It is simpler to use chemical energy than it is to use sunlight in terms of biology. So it's interesting that there may be chemosynthetic organisms on Titan. So that's a good point. Chemosynthesis is a good and plausible energy source.
One more from Pawan Shakawat. What if we are looking in wrong direction? Maybe life is there entirely different from our planet, non-carbon based, different conditions of survival, etc.
Yeah, I hope somewhere that is true, and we find life somewhere that's very, very different. But right now, we can barely know enough to look for life like us. We have no idea how to actually look for life. I could not go to NASA headquarters and say, here is a mission designed to search for life as we don't know it, because I don't know what instruments to put on that mission. So it's a practical problem. The search for life is restricted somewhat narrowly, purely for practical reasons, not because of some fundamental understanding that life must be this way or that way. I don't think we can rule out anything. When we only have one example, we can't rule out anything.
Yeah.
But
that's a very, very interesting question from Anurup Mohanty. Director of Dr. Mckay, will Enceladus ever become dry as it is constantly losing water?
It's losing water, but over the lifetime of the solar system, it's only lost 10% of its water. So it won't, it'll live for a long, long time.
Yeah.
Long enough for us to get there and take a sample.
Yeah, okay. There's one another question. We don't really know what Luca on Earth was like. The last universal common ancestor on Earth was like. There are only assumptions and theories. So what is your comment on that?
That's a good point. And it may be that we will know more about the early tree of life on Earth when we have another tree to compare to. When we have more than one Luca. Imagine, instead of just one tree of life, we have two. One for Mars, maybe even three. One for Mars, one for Earth, one for Enceladus. Then we may be able to answer questions that right now we can't answer because we only have one example. Maybe the properties of Luca is one of those questions.
As one more question from Hima Chopra, is Enceladus having its own magnetic field? But I would like to add one more point here. Do we need a magnetic field for life to sustain?
No and no. The answer to both questions is no. Enceladus does not have a magnetic field. It's too small. The core is not active. And we don't need a magnetic field for life to on Earth even. And the easiest way to see that is to realize that Earth goes through periods of magnetic reversal. And during those periods, the dipole field goes to zero. There are periods in Earth history when the dipole field goes to zero. Now, the multipoles do not go to zero, but the dipole field goes to zero, and then it reverses direction. And those are not correlated with any extinctions at all. Not even extinctions of magnetotactic bacteria. Even magnetotactic bacteria don't go extinct when the Earth loses its dipole field. So there's no evidence that Earth needs a dipole field to support life. And the dipole field does not, sometimes people say, well, magnetic field shields the Earth from radiation. It does deflect solar protons to the poles, creating aurora, but it doesn't actually destroy or shield the Earth in that sense. It just deflects it. And those protons are absorbed by the atmosphere. Even without a magnetic field, Earth's thick atmosphere would provide adequate shielding. So I don't think there's a compelling case that a planet must have a magnetic field to be habitable. And if Earth were to lose its magnetic field, I don't think that it would be a problem, especially since we now don't use compasses to navigate. We use GPS. Who needs a magnetic field?
Yeah. There's a question linked to exoplanets in life from Lux Joshipura. Is there really life possible on the planet Kepler 22b?
Oh, I don't know. In order to answer that, I would need to know more about that planet, which I don't, and I would need to know more about what are the possibilities for life. You could say, is it possible that there's Earth-like life on that planet? And it is the case that some of the exoplanets seem to be consistent with Earth-like life. So I can't answer the question for that particular Kepler object, partly because the Kepler objects are so far away that we don't have detailed data on them. But I know that there are exoplanets discovered, nearby exoplanets, where we know enough about them to know that they are at least within the range of possibilities for life to be there.
So can we take just two more questions? These two are very interesting ones from Akshay Tate. In addition to unusual amino acids found in extraterrestrial space, do we have any idea on the presence of unusual nucleic acids as well? I think he's talking about LND.
I don't know the answer to that. I think the answer is no, but I'm not sure. There's a vast literature on meteorite studies. I'm sure one could find it in that, but I don't know the answer off the top of my head.
Okay. And then the other question is about your field visit. It's from Rakesh Rao. He's asking, were you close to the Maitree station? And
Lake Untersee. It is Lake Untersee. The lake that I showed is Lake Untersee, and it is about 150 kilometers from the Maitri Station. And the experience of diving in it was unlike is like visiting another planet. It's quite incredible, quite incredible. Oh, okay. So you were there when we were there. Okay, very cool. Our PI is Dale Anderson, and I know he has been over to the Maitri Station several times. I haven't been there. I go out to the lake, the trips I've been in, and then I leave. But we did have a visit from a bunch of geologists from the Maitri Station, in the picture I showed. Yeah, cool, great.
Oh, nice. So there's one more question on the fate of Tardigrada or any microbes that has gone with the landers to the moon. What do you think?
Yeah. Microbes, there are lots of microbes on the landers on Mars. For example, Curiosity, it is estimated, had almost 300,000 viable microorganisms on it. 300,000. Now, that sounds like a lot, but in terms of microorganisms, that's a small number. 300,000. The ones that are on the outside of the spacecraft would have died right away on Mars from the ultraviolet light. But any microbes inside the spacecraft, shielded by metal from the ultraviolet light, would still be there. They'd be dormant. They're not growing. It's too dry, but they're not dead either. They're alive, but dormant. And I estimate that there is on the order of about 1 million alive Earthlings on Mars right now, dormant, sitting there, waiting, hoping that things will get better. If microbes can hope, they're hoping that things will get better. They're not growing, but they're not dead. They're alive, they're viable. And we sent them there. And that is what we have to remove if we find life on Mars. That's the undo command, is to pick up all those pieces of every single spacecraft sent to Mars that was not sterilized and bring them back home or sterilize them.
Thanks. There's one more question on the habitable zone from Anurup Mahanti. Dr. Mckay, do you think the definition of habitable zone is vague as Earth lies in the habitable zone, but still we expect to see life in the outer solar system?
Right. The outer solar system stretches the habitable zone concept. Originally, the habitable zone concept was Earth plus or minus a little bit. And that was all very neat. And then we find oceans on Europa and Enceladus and liquid on Titan. I'm not sure that concept of habitable zone is very useful anymore.
Oh, fantastic.
Yeah.
Yeah. So shall we stop here? There's a lot of thanks to you, Dr. Chris, from students.
My pleasure.
Who are watching it online. And many thanks from us. Because given us a lot of details and taken us deep into the second genesis of life. Thank you very much for accepting the invitation. We look forward to interact with you more. Thanks a lot.
Thank you for setting this up. Yeah. I'm going to hang up.
Good night for you.
Good night. Yes.
Right now, 85 current viewers. I'm ending the stream.